Hi, so today we're going to start chapter 5 and we're going to talk about areas and distances under a curve. So here's our first problem. So what we want to do is we want to estimate the area that's under this curved function. So this curved function is the parabola x squared, but I'm only interested in the area that fits between the interval 0 to 1. So I'm looking for this curved piece. Now from geometry, what you've found is that you know how to find the area of polygons, you know how to find the area of circles, but you don't know how to find the area of abnormally shaped functions as such. So what we do in calculus is we take our geometric knowledge and we try to find the area that estimates the area under the curve. So you can see that if I'm going to estimate this, we know first of all that our area has to be greater than 0 because we can't have an area that's less than 0. Now if I were just going to estimate with one large rectangle, and I'd have to find the length and the width of that rectangle. The length and the width of that rectangle each give me a value of 1. So if I find the area, which is equal to length times W, and I take length, 1 for the length and 1 for the width, I would find that the area is about 1 square units. So I know that my area for this region, I know that it has to be greater than 0, but I also know that it has to be less than 1 because this area is definitely smaller than the area of one enormous rectangle or square for this matter. So what we're going to do, instead of just making it one large rectangle, we're going to take this same problem and we're going to break it up into smaller rectangles. Now the first time I do this problem, I'm going to break this into 4 rectangles. So same problem, looks a little bit smaller because I'm zoomed in a little bit more. But I'm going to take this area from 0 to 1, but instead of one large rectangle, I want to break it into 4 rectangles. So you can see that I'm going to cut this bottom or this base into 4 pieces. 1, 2, 3, 4. Now what I'm going to do is I'm going to use the right-handed side to make my first rectangle. So that gives me my first rectangle. I go to the curve and I make my second rectangle. I go to the curve again to make my third rectangle. I go to the curve again and make my 4th rectangle. Now what I'm actually doing is I'm going to find the area of these 4 pieces. So you can see already when I found the area of my very first rectangle with just one big large rectangle, I'm getting closer to what the actual area would be. Now what I'm using is I'm using 4 right-handed rectangles because I started at this side. So I started at the far right hand side and I drew out 4 rectangles. Now each one of these rectangles are going to have a width and they're going to have a height that goes to the curve. So each rectangle is going to have a length times a width. I'm going to do that 4 times. Now since this is my initial position, I'm going to call this x sub 1, x sub 2, x sub 3, and x sub 4. Now, the width of every one of these rectangles are going to be the same. How I'm going to calculate the width of every one of those rectangles is I'm going to find the change in my x. This is going to become my w. My change in my x is going to be that I'm going from 0 to 1, so 1 minus 0, my endpoints, and I'm going to divide that by 4 because I want 4 rectangles. So each one of my w's, each one of my widths here are going to equal 1/4, 1/4, 1/4, and 1/4. Those are my w's. Now what I have to calculate are what my lengths are, or the heights of those rectangles. So since I'm using right-handed endpoints, I'm going to forget about my initial position and I'm going to plug in 1/4 because that's my first x. So I'm going to have 1/4. Since this function is x squared, I'm going to square 1/4. That becomes my height, and my width is 1/4. I'm going to do that for each position. My x sub 2 is 1/2. When I plug it into x squared, that gives me my height times my width. I'm going to do that for my third position, which is 3/4 times 1/4. And I'm going to do that for my last position, which is 1 squared times 1. So quick calculation in this. So I have 0.25 squared times 0.25 plus 0.5 squared times 0.25 plus 0.75 squared times 0.25 plus 1 squared times 1 gives me 1. So I get a total area using right endpoints is 1.21875 square units. Now, as you can see, I have a lot of this area that's an over what I really wanted to estimate. All of this area above that curve is extra. So that's going to make this be an overestimate. All right, so I have a right bounds. Now, I'm going to try to find this area again, but instead of right-ended points, I'm going to use left-ended rectangles. So I start this problem the exact same way. I still want 4 rectangles, but instead of using these rectangles coming from the right side, I'm going to use these rectangles coming from the left side. So since my leftmost point, my initial position, x sub 0, is already at 0, I actually am not going to get a rectangle out of my first one. But my first position, I can get a rectangle. My second position gives me a rectangle. My third position gives me a rectangle. And my last position. So you can see now here are my 4 rectangles. So I'm actually never going to use this point when I do left-ended points, like I didn't use this point when I did the right-handed endpoints. All right, now when I calculate my area, you're going to see that now I'm kind of at an underestimate because I have part of this area that I'm not reaching. That's not going to be calculated in my area. None of this little bit of orange space is going to actually be calculated in my area. But I'm going to do the same thing. I'm going to break it into 4 left-handed rectangles. My delta x is going to be the same thing, which is my width. My change in my x value, I go from my right-handed point to my left-handed point, and I divide it by the number of rectangles that I want. So my delta x every time is still going to be 1/4. It's just where I start. So this time I'm going to start at my first position, which is 0. So I'm going to take 0 squared times 1/4. I'm going to take 1/4 squared times 1/4. I'm going to take 1/2 squared times 1/4. And I'm going to take 3/4 squared times 1/4. So you can see that I'm not having that last position at all. So again, a quick calculation, that first point's going to give me 0. So I have 1/4 squared times 1/4 plus 1/2 squared times 1/4 plus 3/4 squared times 1/4 gives me a left-handed estimate of 0.21 So you can see that that's going to be a low end estimate. All right, so right now what we do know is that our area is going to be caught somewhere in the middle of 1.21875 square units and 0.21875 square units. All right, so our third option here, instead of using right-handed or left-handed, which clearly gives me an overestimate or an underestimate, what I can do is I can actually use midpoints. And what the midpoints do is it kind of equalizes things. So I'm still going to use 4 rectangles, but this time I'm going to use the middle to find the midpoints. So I'm going to cut this into 4 equal pieces again. That means my delta x is still going to be 1/4. But instead of using the right or the left, I'm going to cut it one more time right in the middle. So when I cut it right in the middle, you're going to see each piece of the rectangle is going to have a little bit above and a little bit below. So when I go ahead and I calculate these, it's going to have more of a balance. All right, so when I take my 4 midpoints, this time I'm not at the left-handed point or the right-handed point. I'm in the middle of those points. So if I calculate what's between the middle of 0 and 1/4, that's cutting that in half. So I'm really going to count by 1/8. So I'm going to continue to do that just to make my math a little bit easier. So this would be considered 1/8. This would be 2/8. I don't need that number. I need 3/8 as my next midpoint. 4/8, 5/8 is my third midpoint. 6/8 and 7/8 is my fourth midpoint. So I'm going to take that in that function again. I'm going to take 1/8 squared times my delta x plus 3/8 squared times my delta x plus 5/8 squared times my delta x plus 7/8 squared times my delta x. I'm going to do a quick calculation here in my calculator. So I'll have 1/8 squared times 1/4 plus 3/8 squared times 1/4 plus 5/8 squared times 1/4 plus 7/8 squared times 1/4 to get me an area that is 0.328125. Now you can see if it's easier, you can use that distributive property and pull these 1/4 out and save that for the end. So you can do all of your adding and then multiply your result by 0.32 or by 0.14, or I'm sorry, by 1/4, which is 0.25, giving us a midpoint area that is approximately 0.328125. Now you can see that in my picture that I do have some area that is a little bit over and a little bit under, and that's coming in between where I thought I would be originally. If I go back here, up here and check, my right-handed estimate should have been less than 1. So I'm looking here and I'm trying to see what I did wrong real fast for a correction here. I definitely did something wrong here when I corrected this. +1. Oh, I see. I didn't multiply this last one. Should have been multiplied by 1/4. That is a definite mistake. So I'm going to multiply that whole answer by 0.25. This overestimate should have been 0.46875, which makes this more reasonable. I knew something wasn't working quite the way that it should have been. All right, and that's going to fix where my area should have fell between, and that fixes that this falls a little closer in the middle of all three. All right, now to make this problem even a little bit more accurate, your textbook shows, well, what if we break it into more rectangles? So this is what more rectangles looks like. So you can see the first two boxes here shows a right-handed and a left-handed. This is our right-handed side. This is a left-handed side. And you can see what it looks like if you break it into 10 rectangles. You can see what it looks like if we break it into 30 rectangles. And you can see what it looks like when you break it into 50 rectangles. So the idea here is, well, what if we break that into as many rectangles as we possibly can? The more rectangles you have in there, the less of an underestimate you have, and the less of an overestimate that you have. So if you can make that n approach infinity, then you're even being more accurate to the actual area under that curve. So that takes us to our definitions that you can see on the next slides. These three definitions just talk about what the actual formula is and what we were doing. Now, we weren't running that limit to infinity just yet. We're going to get to that in the next upcoming sections. But what we're looking at here is the formulas that we just used. To find that right-handed area, we skipped over that first position, that x sub 0 position in our function. We started with x sub 1, multiplied it by the change in x, added it to that x sub 2, multiplied that by delta x, and then we did that for as many rectangles as we're going to put into that function, whether it be 4 or whether it be an infinite number. The only thing different when we used left-handed endpoints is that we started at the initial position and we did not start at x sub 1, we started at x sub 0. So you can see that our last position is going to be one less than the number of rectangles that we have. And of course, this is the notation that we're going to use if we're using midpoints. Instead of using the x sub 0 or the x sub 1 as is, we're going to use that starred notation. So this would be the first midpoint of the first rectangle, the second midpoint, and so forth all the way to the end.